So the posterior mean is x plus r over n plus r plus s. And the nice thing is that we can write this as a linear combination of the MLE and the prior mean. So the MLE is x over n, and the prior mean is r over r plus s. And just notice that the n's cancel and the r plus s cancels. So we're always going to have this kind of formula. And the nice thing about this is that you can see that as n goes to infinity, the MLE becomes dominant, and the prior mean basically becomes irrelevant. Furthermore, the posterior approaches a normal distribution. We'll see that its normal maximum likelihood 1 over sample Fisher information. And you can actually just see that when our two parameters are large, that beta is approximately normal. Another example, we have x Poisson, IID Poisson, with parameter theta, where theta is gamma alpha lambda, with alpha lambda known. Then we can write the posterior density is proportional to the likelihood density times the prior density. And notice that when n becomes large, the posterior dominates the prior. In fact, where the likelihood is large, the prior will be relatively constant. And so the posterior is, we showed last time, a gamma sum of the xi plus alpha lambda plus n. And the posterior mean we showed is sum of the xi plus n over lambda plus n. And again, you can write this as a linear combination of the MLE and the prior mean, where the MLE becomes dominant as n goes to infinity, and the prior mean becomes irrelevant. And here's just a picture of a gamma 8 and a gamma 100, and you can see that when our two parameters for gamma become large, approximately the same size, it approximates a normal, and it will approximate a normal MLE 1 over sample Fisher information. So today we're gonna go over section 8.62, talking about a large sample normal approximation to the posterior. As well, we'll talk about the Bayesian approach to hypothesis testing from section 9.1. So we've seen now in a few examples here that the posterior distribution is nearly normal with the mean equal to the MLE, and the posterior SD is close to the asymptotic SD of the MLE. So we have convergence in distribution of the MLE and also the Bayes posterior to a normal distribution theta hat ml 1 over sample Fisher information. So why is the posterior asymptotically normal? So I can only speak in sort of general brushstrokes about this, but but the posterior density we can write as a proportional to the likelihood in prior, and as I said, when n is large, the likelihood dominates the prior, and so essentially we can write the posterior as being proportional to exponential log likelihood. And we're going to write the log likelihood as a Taylor series centered at the ML. And we know that we can ignore the higher order terms because the ML converges to theta. So now when we do this, the log likelihood is a constant plus 0 plus this now second order term. The second term here is 0 because theta hat is the max of the log likelihood. So the first derivative at the ML is 0, and so when we take the exponential of this, we get that the posterior is proportional to the exponential 1/2 theta minus theta hat squared times this term. And if we write that term, which is the second derivative of theta hat ml, as in the denominator, so you can make it look like a normal density. So we have the form minus 1/2 theta minus theta hat squared over minus 1 over the second derivative of the ML estimator. And so now, what is this second derivative of the ML estimator? So we have a trajectory, which is, say, the first element of our of our sample. We have a trajectory of its likelihood, right? It's in fact its log likelihood, and so we're looking at its curvature, and we so this is the Fisher the Fisher information is the expectation of the curvature. Actually, it's minus the expectation of the curvature at the ML, and here the expectation is you're averaging over all trajectories, whereas here in our denominator here we have just the curvature of a single trajectory, but that's an so they're close. An expectation. So the average curvature is an approximation to any given curvature. So they're not that far off, and so in that sense, the posterior is normal, theta hat, 1 over minus this second derivative of the log likelihood at the ML, which is approximately, the variance is approximately 1 over the sample Fisher information. So that's all I have to say about parameter estimation in the Bayesian world, but it complements the frequentist world, and I hope that you'll learn more about it in your next class. I want to briefly just talk about Bayesian approach to hypothesis testing. So remember, the frequentist approach is also called the Neyman-Pearson paradigm. Here we have a decision to reject or accept the null. We also have errors with that decision, and type 1 error in particular, alpha, is something we want to control. So that's when the null is true and we reject. So now our test is going to be to reject the null if lambda, which is the ratio of the likelihoods, is less than c. And so this ratio of likelihoods is the probability that the probability of x given the null over the probability of x given the alternative. And so you would want to reject the null if this ratio is small, because if the probability that you have x given the null is small, then you probably don't have the null. So let's just take a look at an example. We've seen this before. Suppose you have two coins. Coin 0 has probability 0.5 heads. Coin 1 is probability 0.7 heads. You don't know which coin you have. The null is that you have coin 0. The alternative is that you have coin 1. We can write down these log likelihoods just using the binomial formula. Write down our test statistic lambda here. And so, as I said, the likelihood ratio test says that we're going to reject if lambda is less than c. Now, in the frequentist framework, c is determined directly by alpha. And so, for example, if alpha is 0.5, you see that c is 1.984. And so this gives you a cutoff, or a rejection region. Now, in the Bayesian approach, instead of alpha determining the cutoff, the priors, the probability that you have the fair coin and the probability that you don't have the fair coin, determine the cutoff. So the Bayesian LRT is that we reject the null if the posterior ratios is less than 1. This totally makes sense, because if the posterior is small, in particular less than 1, means that it's less likely that, given the data, it's less likely that you have the coin 0 than coin 1, then obviously you would reject the null. So we have the same table as before, but to write our posterior ratio in terms of lambda, we can just use Bayes' rule, and we get that it's lambda times the ratio of the priors. And so another way to say this is that we reject the null if lambda is less than probability that you have h1 over the probability that you have h0. So this ratio of priors is our cutoff. And we don't involve alpha. It's not asymmetric. There's something very pure about this. So then, of course, you still have alpha and beta errors. Alpha is the probability that you reject h0 given that h0 is true, and you can find that. So for example, in this case, if the probability that h0 is equal to the probability of h1, so let's say you don't have any opinion about whether you have coin 0 or coin 1, then we reject if lambda is less than 1 given the null, and you can check from the table that this is alpha is 0.5. Okay, guys, that's the course. I will see you on Monday for a review. Have a great weekend.